Been trying to do that since last year. All right, so graph what we call the greatest integer function. Okay, we talked about piecewise functions a little bit last week. I'm going to give you guys in an email later today this GeoGebra. It allows you to maybe graph some piecewises a little bit easier than what we've done in the past, or not what we've done in the past, but maybe what in regards to just using GeoGebra from kind of like just a fresh start with GeoGebra, or something that hasn't been already created for you. It's kind of hard to type in your piecewise functions. If you try to use your TI-83 or 84, you have to use what's called Boolean notation, which is kind of a pain in the butt. So I structured this. I tried to create this. Hopefully it helps you. It only right now has 3 inputs. So if you had a function that has 4 or 5 different rules, you could maybe run into issues. But this will work for anything that has 2 or 3 rules for it. Just kind of show you how you would do this. You know, maybe one of my rules is 2x. Okay, but I only want to look at 2x. If I graph that, obviously it's going to give me the whole line, right? If I want to only show that for x values that are greater than 2, this is how I would do that. I would put parentheses x greater than 2. I would put that restriction on, and it will then just give me the curve for greater than 2. Does that make sense, everybody? So it's pretty nice. Don't worry about this other stuff in here right now. I'll clear that up for you. Let's say I want x squared. Well, let's say I want x squared on the interval of -2 to +2, but I want to include those. Okay? The way I do that in GeoGebra is I just go -2. I say less than or equal to. And then I go x less than equal to, and then my other value. A lot of times with computer programs, math related, if you want less than or equal to, that's the notation you have to use. GeoGebra does a nice job though. When I hit enter, it actually transforms it into that symbol that we're accustomed to. Okay? And you see that it graphed that thing only for the x values between -2 and +2, right? Let's say I want the graph, I don't know, 2x. Now let's go maybe 1/2 x plus 6. Okay, but I only want that for values that are maybe less than -4. So x is less than -4. Hit enter. Okay. What is going on here? That should be all right. I don't know what's going on, what I've got this showing up for. I'll fix it. But that should not be there. X is less than. Okay. So I just changed the function just so you can see the full piecewise. I think maybe the coding I've got in the background for those input boxes is referencing something that it shouldn't. So I'll fix that and I'll get that out to you. But you can see then, like on homework, if they're asking me to graph something, I can type those in pretty quickly and see if that graph is what I've come up with by hand. Is that all right with everybody? Otherwise, it's kind of like I said, TI-83, 84. There is notation for you to be able to do that. But it'd probably take us maybe half hour to 40 minutes to really learn that notation. You can same thing. I mean, if you want to, you can kind of see what's happening over here in GeoGebra. If I had just a blank new GeoGebra, you could do the same thing and say, okay, my 3p. Let's say I want an x squared. I can just hit x squared, and then in parentheses put -2 is less than x is less than 2. I can just do that individually. Okay, does that kind of make sense? So you got a couple different options maybe that you can use. I'm not 100% sure what's going on down here when it just makes that green, but it's always going to revert back to the x-axis and make some green highlight of the x-axis. Don't worry about that though. Okay, so this is the graph that we're interested in here. All right, so that is going to be sent out to you, like I said, later once I get that fixed. There's something else we talked about, which is another. It can be defined as a piecewise function, but we're going to deal with it kind of using our technology and maybe even eventually by hand. It's not too bad, but it's a new function that you've never seen before. It's called the greatest integer function. Okay, and it's actually pretty easy to evaluate at. Okay, so the algebra is not hard here, but we have a couple different functions that we're talking about when we talk about this structure. Okay, when we talk about the greatest integer function, sometimes it's referred to as the floor function. Okay, basically what's going to happen here when we say greatest integer function is that whatever your input value is, you're going to round down to the previous integer, unless it is an integer, and then it kicks back as an output that integer. Okay, so for instance here you see they're using 2, okay, as my input. So I put 2 into this function, and because it's an integer, it just kicks back out the output of that integer. So 2 gives me 2. Does that make sense? So it gives me the 0.2 comma 2. Okay? But if you see 2.3, 2.3 is my input. The output then rounds it down to the last integer, which would be 2. Okay? 1.999999999, however many nines you want to put on there. Okay? The last integer you would have passed through on your way to 1.999999 on the x-axis would be 1, wouldn't it? You're always round. The greatest integer function says always round down. Okay. So it rounds it down to 1.0002. Okay. Rounds down to the first integer to the left of it would be 0. And now this last one, this is the one people struggle with. Okay. If I'm at negative 3.5, the idea, and regardless of whether it was negative or not, even if I go to the 1.9991, let's say this is 1.999 here. Okay, so let's say that 1 is here. As I'm moving along the number line and I get to 1.9999, what was the last integer I passed through left to right? It was 1. So it's going to return back to that 1. So if I'm at negative 3.5, going left to right, and I'm stopping right there, what's the last integer that we passed through? Negative 4. It returns back that previous integer that you passed through left to right. Is that okay with everybody? A lot of people want to return negative 3 on that one. Okay? So we're always returning the integer to the left of whatever real number you have. Okay? Unless it is an integer, and then you should return that integer. Okay? A lot of times the greatest integer function is referred to as a step function. Okay? And you'll kind of see why when I give you the graph of this. Okay, so this is that function. All right. Now it's a little bit different notation that Algebra uses, and really any other math program is going to do this. The notation I gave you in the last slide was the greatest integer function. It's kind of a weird bracket with that extra line in it. And then, obviously, the same thing going the other direction. A lot of times, because of this idea that we also call this thing the floor function, the notation can change to this, where you still kind of got the same type of brackets, right? But the floor, the bottom of the bracket, is the one that's squared off. So that kind of visually reminds us that we're returning the smaller value, or the value to the left of wherever we're at. Does that make sense? Okay? So it's kind of giving you a visual to round down when we're dealing with this. So this is what happens. If I think about looking at, let me see if I can make my my ordered pairs a little bit larger for you guys. Options, labeling, ones. All right, so you're seeing kind of that crosshair being what's identifying ordered pairs for me, right? Okay. If I see negative 1.8, that's my x value that I plug in right here. Okay. So if I plug in negative 1.8, okay, the integer to the left of that would be my negative 2, correct? So that's why we're seeing a negative 1.8 returns a negative 2. All right. If I get all the way up to negative 1, you see how it jumps me up to the next step? Okay? Because when I evaluate negative 1, what's the greatest integer function do? If it's an integer we put in, it kicks back the same integer. Okay? And then everything in here, you know, negative 0.6, 61 is going to return a negative 1, right? It's going to return that previous integer that we passed through. If I start working on these positive values, okay, you know, positive 1.8 returns a 1. Positive 4 is going to return an integer of 4. Okay, and I can slide this thing through and see that 4.67 is going to return 4. Is that okay with everybody? This is a function, okay, because of the idea that when it's an integer, it returns that integer, okay, and we're rounding down. So if I had like 3.9999999999999, it's going to return 3. When I have 4, it's going to return 4. So I can never, ever, ever, ever put in the same input value and get 2 returns for it, right? 2 outputs that are different. So this thing passes the vertical line test everywhere, okay? Even though it looks like we got a lot of points that are overlapping, there's an open dot here and a closed one dot there, so it does pass the vertical line test there. So that is what we call the floor function, okay? There's another function, okay, and it's kind of the idea of, okay, now we've been able to round down. Should we be able to kind of use the same logic and round up? So we round up, we get what we call the ceiling function. And now you see the bracket squared off at the top, right? So hopefully that gives you the idea that we're going to round up no matter what x value we have, unless it's an integer, and then return that integer, okay? So if I'm at 0.2, round it up, you should get the next integer to be 1, right? So x value of 0.2, our y value is 1. All right. If I go to 1, okay, take my cursor and go to 1, okay, you see that it's inputting an integer, output that same integer. Then when I go to, you know, anything 1.7, okay, round up to 2. So x value of 1.7, y value of 2. All right. And that's called our ceiling function. Is that all right with everybody? Okay. Now let's talk about where maybe you guys have recognized this or ran into this type of function at some juncture of your life, and it is I guess before we get to this, you guys can look at the piece, and this is why we talk about it in regards to dealing with piecewise functions. Could I write this function and say that, and do my piecewise notation, f of x equals, okay, could I say 1 if x were between 0 and 1? Could I say then, let it be 2 if it was between 1 and 2? Could I say, let it be 3 if it's between 2 and 3? Does that kind of make sense to everybody? So if I choose an x value that is between 0 and 1, okay, choose any x value between 0 and 1, return 1. Does that give me that little segment right there? Okay. If I then say, and if I choose 1, I got to get back 1. Come down here to this one, it says, okay, choose an x value between 1 and 2. Okay, well that means choose maybe that value right there, 1.3. Well, if I put 1.3 in, it says return 2. So give me that little point right there, correct? And it will eventually fill in that segment if I use all these x values that are inside that interval. Same thing here, between 2 and 3. Okay, so the step function, the ceiling function, can be written as a piecewise. Does that make sense to everybody? Okay, and basically each one of those little segments can be written as a rule. Where have you seen this maybe most obvious or most impactful to you, I guess, would be in a situation like this. Okay, this is, again, we got it piecewise here. Okay, and the open dots, closed dots, those are just things I put in on top, so they kind of run out at some point. But you see that on those blue segments, the endpoint to the right should be open, and the endpoint to the left should be closed on all of them. Let's say that my x-axis is in units of gigabytes, and let's say my y-axis is in units of dollars, but let's say it's in tens. Okay? So where I see that green line, it's going through 5 on the y-axis, but because it's in tens, let's say it's 50. Does that make sense? Okay. And this maybe is comparable to what you guys see on like a cell phone bill, okay, or your parents see on your cell phone bill. You have a base rate, okay, maybe within 8 gigabytes. Okay, so whatever your data plan is, you're going to pay $50. Whether you use 1 gigabyte, 3 gigabytes, 7 gigabytes, 7.99999 gigabytes, you are using under 8 gigabytes, you pay $50, right? But the instant that I hit 8 gigabytes, what do they do to me? They charge you anywhere from like 10 to 15 bucks, right? Okay, so let's just say right now, we're looking at that graph, they jump me up to 60 bucks, right? And they're going to charge me now an extra $10, okay? So what happens then is that within that 9th gigabyte, okay, so this blue, where my cursor is, that blue segment is representing that 9th, any portion of that 9th gigabyte, right? And basically what it's saying is if I use 8.1 gigabytes, I'm paying the fee for using 9. Does that make sense? Okay, or I'm paying for that one complete whole extra gigabyte regardless of how much of it I use. Okay, so if I use 8.1 or if I use 8.999, I'm going to pay the same extra 10 bucks, right? Does that make sense to everybody? Okay, but the instant I jump to 9, okay, what's it going to do? It's going to jump me up and charge me another 10 bucks, right? And now I have to pay that extra 10 bucks regardless of how much of that next gigabyte that I'm using. I think I'd be on the 10th gigabyte, the portion of the 10th gigabyte would be what I'm on, right? So this is a step function in regards to your data plan. And that's how Verizon or Sprint or any other phone carrier will charge you, okay? And hopefully you understand maybe the logic of why they do it. There's probably a couple reasons. But think about, just the high schoolers in this high school. Probably most of them have a cell phone, right? So we're saying maybe 400 students have a cell phone. Every one of those probably going to end their cycle on a different day, okay? And are they all going to probably end their cycle at a different maybe megabyte in that next gigabyte? Does that make sense? So somebody might finish at 8.1, somebody might finish at 8.25, somebody might finish at 8.376. So we're all finishing somewhere different, right? It would be logistically a nightmare for Verizon to have a program that codes and says, I'm going to collect all that data from each individual person and then prorate their bill based on how much of that next gigabyte they've used. Do you see how it's so much easier to just say, okay, this person used 8.2, let's charge them for 9. This person used 8.4, let's charge them for 9. Isn't that a little bit easier? And what happens to them? What happens to Verizon if they do that? They're making more money off of everybody, right? Okay. No matter how much you use of that, if you use 8.9999999, they're still getting you for 0.00001 that you didn't use, right? So they're making money off of everybody, regardless of how much of that next gigabyte they use. Okay. So this is something, and you guys probably have never done this before, but long distance phone calls are kind of the same way. Attorney fees sometimes are the same way. Okay. You have what we call a retainer, okay, which basically is just a base rate that you pay them to keep them on as your lawyer. But then when they start doing work for you, that rate increases, okay, on top of that retainer. So there's a lot of things that on a regular basis that financially we account for with greatest integer functions, okay. Now writing this one, and this is kind of how the programming for Verizon would be in their billing department is that you got that piecewise function where the first 8 gigabytes is just $50. Okay, and then after that, we start climbing up that step function. Is that all right, everybody? Kind of visualize what that is. For the most part, what your homework with when you see a greatest integer function is that they're going to give you maybe something that looks like this. This thing here in blue, okay? Where it's just like the order of operation. It's just like if I were squaring something, like it was x minus 8 quantity squared, or if it was square root of x minus 8. Order of operation says plug into here first, right? So let's say x is 2.3. I take 2.3 and I subtract 8 from it, okay? I get that value and it says this is the floor function, so now it says round it backwards, right? I would then round that value backwards, and once I get that integer, add 6 to it. Does that make sense? So you evaluate these things just like you would evaluate any other function. Order of operations is going to take precedence, but the notation here, that floor function says round backwards. If it was a ceiling function, it would say round up, okay, or forwards. So that's the greatest integer function. The next thing I want to talk about is what we refer to as increasing and decreasing function. We're going to spend a couple days on the information that this attaches itself to, or the different places that this is used, and the importance of it. A lot of our calculus is structured because of this idea, and it's not really hard. It's actually a very simple concept. You guys know when we look at a line, whether it's moving up from left to right or down from left to right, correct? So you can tell if it's moving up left to right that it's increasing, correct? You can tell that it's decreasing if it's going down from left to right, correct? Okay. Up. Yep. Yep. Back. Just stop right off this class. So increasing, decreasing. We can do that with lines pretty easily, okay? But we should be able to do it with all curves, okay? So the visual of increasing means that as I move from the left to the right on my x-axis, from left to right on my x-axis, we are increasing if your y values are getting sequentially bigger, right? Does that make sense? Okay, one after another getting larger. So between A and B here on this interval, we would be increasing because we see our y values are getting larger and larger. Okay. At B, at point B, something happens. Okay. And we are no longer increasing or decreasing. Okay. We'll talk about what that point is later on. But then to the right of B, on this interval, B to C, okay, our y values are getting from left to right. They're getting smaller when I compare them, right? Okay. And then in that last interval, we're doing the same behavior that we did at the beginning, so we're increasing again. What happens, guys, is they're going to ask us, when is this function increasing and decreasing? Okay? And when they say when, they're asking you for what x values is this thing increasing and decreasing. So our answer for increasing and decreasing functions, the way we'll identify it, is that we're going to identify a domain. This is the domain. These are the x values that this thing is showing this particular behavior. The behavior is then, or that domain is decided on the behavior based off of what the y values are doing. Okay? So your y values tell you whether you're increasing or decreasing, but you record that and identify that based off of the x values as an answer. Okay? So we'll do some examples of that tomorrow. But I want to get into, in 2 minutes, kind of talk about the way we have to define this mathematically. It's not hard to think about what increasing, decreasing means visually, but we have to be able to describe that mathematically. We have to have this the definition of what we mean by increasing. Okay? We have to write it this way so that there is never, ever a situation where we accidentally categorize a situation as being increasing or decreasing when it's not. Okay? That's what definitions are, right? We write them so they're structured so nothing accidentally gets classified as something else. So the way we do that here is this type of notation. We say on the interval of I, you're increasing. If you have x values, basically what we're saying here is that your first x value on your x-axis is smaller than your second x value. Does that make sense? So we're reading this left to right. If our x value to the left is smaller than our x value to the right. So an x value here, maybe that's x1, Maybe this is x2 right there. Okay? They're saying if you plug in those x values, whatever they are, to your function, okay? If you evaluate and get f of x sub 1, so that y value right there, and it is smaller or less than, when you evaluate that y value right there, if that happens, then the situations you have occurring between your x1 and x2 is that your function is increasing. It's on the rise. Because your first y value was smaller than your second y value. Does that make sense? Okay? And then the idea is that those x1s and x2s, we want those infinitely close together. And then we're going to keep repeating this over and over and over again until we see that change from being less than, for our first y value being less than our second y value. Okay? Because when that changes, we're going to start getting something like this. If our first x value inputted into our function provides a larger y value than our second input value or second x value does, then we're on the decrease. Does that make sense, everybody? Okay. But that's the way we have to describe it mathematically, so that nothing accidentally occurs. Okay. Nothing like, well, what happens if we're doing neither of those things? Okay. So if we're not doing any of those things, we have what we call maximum or minimum. Okay. It's the change from increasing to decreasing. We wouldn't want one of those situations to accidentally get classified as decreasing or accidentally get classified as increasing. Okay? We'll pick up with this tomorrow. We might do a little fun exercise tomorrow too.